Finished up talking about this on Friday. Basically, a partial sum is exactly what it means. Partial means parts, right? Okay. So you're summing up parts of your sequence. Okay. And usually, what we do is we like to be very systematic about it. So we start the first term and then go to the second one, third one, fourth one, whatever. If I want S sub 4, like I said, starting the first term, adding together the first, the second, the third, and the fourth. If I wanted S sub 7, it's adding the first, the second, the third, the fourth, the fifth, the sixth, and the seventh, right? Okay. I'm continually adding however many they want me to do. Okay. Now, there are questions that arise eventually that says, maybe I want just the sum of the 7th through 15th terms. Okay. That's not really that difficult. What you do is you find the sum of the first 15, and you find the sum of the first 7, and what do you do with those two numbers? Subtract. Okay. And that will give you the 7th through, actually it would be the first, we want to do 1 through 15 and then 1 through 6. And then subtract those, and that would give you the sum of 7 through 15. We're not going to get into that, okay? There is actually a better way using sigma notation to do that as well. But partial sums is just adding up, in amount or in objects out of your sequence, okay? And we go in order from 1 to 2 to 3 for that n value. So here's an example. They give the rule for a sequence as 1 over 2 raised to the nth power. So if we look at the sequence that's created, it's 1/2, 1/4, 1/8. Next ones will be 1/16, 1/32, 1/64. Okay. So when they want, it's kind of trivial when they want S sub 1. S sub 1 is simply just the first term. There's no addition there. Okay, it's only one object. When they want S sub 2, taking S sub 1, A sub 1, and adding to it A sub 2. Add those together, you get 3/4. We want S sub 3, so it's the first term, the second term, and the third term of our sequence. Find a common denominator, gives me 7/8. S sub 4, first term, second term, third term, fourth term, and together you get 15/16. Is that doable? The only thing with this is, and obviously you can use your calculator or whatever, it's coming up with that common denominator of 16, or if it's, this sequence is not that hard, your common denominator is always going to be that last, your last denominator because of the way of 2n and how that works and the number of multiples of 2 you have in your denominators. There's another sequence. They just kind of ask you to find the partial sums. And this kind of happens quite a bit. If you look at the terms there, A sub 1, A sub 2, A sub 3, A sub 4, and A sub 5 graphically, and then you look at the sums of S sub 1, S sub 2, S sub 3, S sub 4 graphically, and I plot them against each other or together, they turn out to be kind of parabolic there, don't they? And that's kind of a neat relationship there, at least for that partial sum. We'll talk about what divergent and convergent means more detail tomorrow. All right, I want to get down to sigma notation. Okay, and this is just summing things together. Sigma is a Greek letter. This is actually the cap down in the bottom in that blue box. That's the capital letter sigma. But for us mathematically, it means summation. Okay, it means you're adding things together. And what happens is, it is actually, in calculus, there are two operations. Differentiation, which is the process of finding slopes. And then there's one called integration, which is the process of finding areas. Okay? Sigma notation is kind of the introductory foundational concept that allows you to do what we call integration. Okay? What happens with, just give you kind of a quick rundown of why we talk about sequences and why we talk about summations, is gearing us towards calculus. In calculus, let's say I've got this curve. It might look something like that. And integration is simply saying that we are interested in finding, maybe on some interval, maybe I say this interval here, from A to maybe that interval B. And I create vertical lines there. Okay. What we're interested in is being able to find eventually the area underneath that curve and above the x-axis. Okay. And integration is the process of doing it. Okay. It also allows us to eventually find volume. But in order to do that, that's not a really nice geometric shape, right? Okay, like if it was just a rectangle or a triangle or a trapezoid, we have really nice geometric formulas to be able to find those areas, but that's an irregular formula, okay? So what we end up doing calculus-wise is say, okay, we can get an approximation of that area by breaking that area up into these things called, what are those shapes? Rectangles, right? Okay. And maybe this rectangle there is our first rectangle. Maybe that one's area is our second rectangle, third one, fourth one, fifth one, right? And can we add those 5 values up, those 5 areas? Because finding the area of a rectangle is pretty easy, right? Okay. And you'll walk through and talk about how you find the length and the width of those. But we add those up, and that gives us an approximation of the area under that curve, right? Okay. And then we start thinking, okay, if that's an approximation, how can we do a better approximation? And the way you do a better approximation is that you make more rectangles. You make the width a little bit more narrow, and each one of those allows you to fit in more rectangles, right? And the idea eventually is that you make the width of each one of those rectangles infinitesimally small, okay? And that will give you then the exact area underneath those rectangles. So what we want to do is eventually put an infinite number of rectangles in here. And then that would mean that this n right here in our sigma notation becomes infinity, and then we address that area that way. Those are called Riemann sums. When you get to calculus, you'll talk about those in great detail. And again, you'll talk about sigma notation and how to address it and the notation and what it all means to you. But you might see some sigma notation in your homework, so I won't talk about that. Basically what it is, you've got the sigma, the symbol. Okay, so when we say sigma, we're talking about, that's the capital letter right there, sigma. Everybody okay with that? Okay. And it just means summation for us. This here is what we call an index. Okay, essentially being a counter for us. Okay, telling us what term we're currently interested in. Okay. And that index is going to go from, we can start at anything we want to, usually start at 1. We'll see examples where we start at 3 and 5 and whatever. But you start at your index. As basically, that's going to be, that k right there is going to be related to the variable component inside your rule. Okay? So a sub k is a rule for us. And then this number up here is kind of the upper bound for our counter, meaning that we're going to start at 1. And we're going to keep going in iterations. We'll go 1, and then we'll say k is 2, and then k is 3, and then k is 4, all the way up until we reach whatever that number is right there. Okay? Now, for the most part, what we do right now, that number is going to be finite. It's going to be like 10 or 12 or whatever. Tomorrow, that number you see on your practice exam, that number is infinity, right? Do you ever want to add infinite numbers together? Will you ever be able to do that? No. So when we see that, there's going to be some formulas that allow us to add up an infinite number of values. Okay? But we have to determine what kind of sequence we have in order to do that. But if you look at this, all we're doing, if k is 1, we put k right there, and the first term becomes a sub 1. If k goes to 2, we put 2 right there, and it becomes a sub 2. If k goes to 3, we put 3 right there, and we get that term a sub 3. And we keep doing that until we reach that n value. Once we do that, we have all these numbers listed down. We just simply grab our calculator, add them together. Is that doable? Now, calculus-wise, there are a lot of great, nice, clever techniques. There's kind of like a whole section of algebra with sigma notation that allows you to do that summing procedure a lot easier. We don't get into it in this course. They don't ask us to. But know that, if this n is 100, I've got, like 2n squared plus 1 is my rule, I'm going to have 100 terms that are really hard to deal with. But there are some calculus and algebraic principles that allow us to do that summation much, much, much quicker than writing out 100 terms and adding up 100 terms. Does that kind of make sense? And you'll get into that when you get into calculus. So this is just revisiting the vocabulary for sigma notation. Whenever you see the word index, in math, it's index for like a textbook is showing you where something is, right? Okay. You look up the index, tells you what page that object is on. Well, index algebraically or mathematically is the same concept. This is my index, and it's telling me what object I'm at or the location that I'm at in my list, right? So whenever you see that word, it's telling you a position, sometimes referred to as maybe a counter, or a counting device to get you from one position to the next position. So that's where we start. That's where we're going to finish. Okay, sigma tells us to add, and this here becomes your rule. Okay, a sub k can be anything, any algebraic expression that you see fit or the author sees fit to put in there. And sometimes we can look at a sequence, and looking at the sequence, we're able to work our way backwards and find the sigma notation for that sequence. In this case, basically what we're doing here, this k squared here is the rule that is providing our sequence. Does that make sense, everybody? So our sequence is going to be, if k is 1, our first term in our sequence is going to be 1 squared. If k is 2, our second term in the sequence is going to be 4. If k is 3, our third object in the sequence is going to be 9, right? So we can see what that list is going to be. 1, 4, 9, 16, 25, 36, so forth. Okay? But the way this is written is that we're interested in k being 1 and going to 5, right? So it means we're really only interested in the first 5 terms. And then the sigma tells you you're doing a sum, right? So you see that they're asking you to do the partial sums, or partial sum of the first 5 terms. That kind of makes sense, everybody? Okay? So all you do is you use this k equals 1 as your input value into this rule. Okay? So I put 1 in there, I get 1 squared, and I write that down. The fact that it's sigma tells me I've got to put a plus sign, and now I always increase my index by one number, one integer. Okay? So I go from k being 1, now I'm going to go k being 2. Okay? Plug 2 in here to the rule, and you get 2 squared. Okay? If you remember, we talked last week that for a sequence, your input values, sequences are essentially functions, and your input values are the natural numbers, right? So that's why we use 1, and then k being 2, and then k being 3, k being 4, k being 5. And when we do that with 2, 3, 4, 5, we should get that sum. Okay? Simply evaluate those, and you get 55 as the sum of the first 5 objects in that sequence. Is that something we can do? Okay. If you look at B, okay, this is one where we don't start at 1. They're asking us now, what is the partial sum of the third, fourth, and fifth terms of I over j? Well, if I look at this, j being 3, my first term, over j. My first term is going to be what? 1/3. My second term is going to be 1/4, and my fifth term is going to be 1/5. Can we just sum those again? Is that pretty straightforward? Pretty easy? Okay. The one thing I want to make sure we understand is when we see something like this, and this kind of maybe leads us into some calculus principles that make sigma notation a little bit easier. Right there, there's no place, my index, sorry. my index is I, okay, or using the variable. But if I look at my rule, is there anywhere to put I in? No. So what we're saying here is that our sequence is simply kind of a constant sequence. Okay? Plug I in here as 1, and you get back what? You just get back 2. Okay? If I plug, let's I go to 2 then. Because remember, I is telling you the position that we're interested in our sequence, right? So the first position when I is equal to 1 is 2. The second position when I is equal to 2, what is it? It's 2 again. And I'm going to keep doing that. Third position will be 2. Fourth position will be 2. Fifth position will be 2. Sixth position will be 2. And if I add those up, what do I get? 12. Okay? Now here's a quick formula that allows us eventually to maybe do sigma notation a little bit easier. What is another way of finding that 12? Taking those two numbers into multiply. Okay? You're going to find out that, and I'll show you these rules, but we're not going to dig too far into them because of other things I want to cover today. But here are some principles that we're allowed to do. And this happens a lot with kind of the operations that we do in calculus with certain objects, is that if I have a, let's say we've got, sigma from, let's just go k equals 1 to do an easy one, 3. Let's just write 2k plus 4. Okay? What this rule here is saying, now you don't have to write this down, just kind of watch. What this rule here is saying is that you can actually, because you have a sum here, okay, inside your expression, you will find out, and we can prove it, that that is the same thing as rewriting as the sum of 2 times k, plus then k equal 1 to 3 of the sum of just 4. Does that make sense? Okay. So why is that nice? Is now that is nice because we can now address kind of the idea that we just talked about. If this is constant, what is that portion of this summation going to lead us to? If I multiply the 3 and 4, what do I get there? I get 12. So I know there is some amount 12 that's existing here, and it's being taken care of by that right there. Does that make sense? Okay. Now we go a little bit further. We look at this one here, and basically what this says, if you've got a scalar multiplier, like this 2 here, you can actually bring that 2 out in front. You can factor it out essentially, and you can do that. Okay, so now I just basically have k here, right? Well, this is kind of easy to do the summation of k from 1 to 3. K is 1, we get 1, right? If k is 2, we get 2, right? If k is 3, we get 3, right? So it gives me what? 6. Okay, so this amount here changes to 6. We've got the 2 out in front, and then we got this 12 that came in the back, so it would be 24. So if you were to write those 3 values out for that summation and add them together, you get 24. Okay? Now, I don't know, in regards to just because I use the small value of k, it might actually be quicker to go through this route and just write it down, right? But if k is 30, I don't want to have to write down 30 terms here, do I? Okay? And what happens is that there's actually a formula that is pretty easy to develop that tells us when you have the summation of k, okay, this is how you find that summation. It's really quick, easy formula. Okay? So, that's kind of the task that you might be set on when you first introduce sigma notation and how you will use sigma notation in a calculus course. Okay? Is everybody okay with that? All right, that's what I wanted to provide you yesterday when I sent out the email on Sunday that I wanted you guys to watch some videos. Anybody get those emails? Okay. I sat down yesterday to try to do some of this stuff, and none of my PowerPoints would download at home. My tablet wouldn't work, so I had a really hard issue with effectively providing you videos, so I did. 13.2 talks about arithmetic sequences. These are really easy sequences. These are all the sequences that we talk about They're, I think, the simplest in nature, really easy to identify, and it's simply the fact that from term to term, the difference is always the same, okay? Call it common difference, okay? If I look at that term and that term, okay, to go from the first one to the second one, you added D, right? Okay? If I go from that term to that term, what did you add to the second term to get the third term? Excuse me. Thank you. If I have A plus D and I get A plus 2D, what did I add to the second term to get A plus 2D? Which is D, right? Okay, it's essentially A plus D, right? And we combine like terms. And then I add what to that term to get that D again, right? So you see that we have essentially written out in generic format what an arithmetic sequence looks like, okay? You're simply adding the same amount from term to term to get the next term, okay? So its sequences like 2, 4, 6, 8, 3, 6, 9, 12, 5, 10, 15, 20, 25, 30, okay? Those types of sequences are arithmetic, okay? The first term a lot of times is called A. I like to put the subscript A sub 1, just to remind us that it is in fact the first term. N is the index of what term we're looking at. So a lot of times when we're developing a rule, it stays as N. We don't change it. And then D is the common difference. D is what you're going to be able to recognize from your sequence, and you'll be able to calculate that and plug that value in. Every single arithmetic sequence is of that nature, okay? So once you plug those pieces in, you will have a rule for your arithmetic sequence. And that's what I was talking about on Friday, where some sequences are very hard to look at and develop a rule, right? You might have to mess around with it 2, 3, 4 times. You remember the one we did on Friday dealt with fractions, and we had to look at how the numerators were odd numbers. So how do we create odd numbers? 2n minus 1, right? And the denominator were even numbers, and we create those by 2n. And that was the rule. That was hard to come up with. But if I recognize a sequence is going like 2, 4, 6, 8, or 5, 10, 15, 20, now that's arithmetic, and it's going to fit that formula. I plug things in, and I now have the rule for that sequence. Does that kind of make sense? Okay, so let's do one. Let's go. Let's see here. They start us with, I'm just going to delete the solution here, but they start us with this sequence here. Okay, 13, 7, 1, negative 5. Just make sure that your common difference is the same between all terms that they provide you with. Okay, I've seen textbooks kind of get tricky, and they'll go like 13, 7, 1, and you say, okay, between the first two terms and between the second and third terms, I have a common difference. That's, in this case, negative 6. And then they'll go 1, negative 3. And that common difference is not the same anymore, right? So it's got to be, the common difference has got to be the same between all the terms that you see provided. Okay? If we look at this, we're assuming this is arithmetic, and we see the common difference in this case is what? Yeah, negative 6, right? You're subtracting 6. So your common difference can be additive or it can be subtractive. So in this case, we're going to write our rule. A sub n is equal to a sub 1 plus n minus 1 times d. Okay? So a sub n, what's a sub 1 in this case? 13. Plus then n, like I said, stays n. And now what's your common difference? Negative 6. Okay? And I should probably write it down. If you want to leave it that way, that's fine. Okay, I think website might ask you to simplify it. So go ahead and distribute, combine like terms, that kind of stuff. So you get 13, well, minus 6n plus 6. So we get 9 minus 6n. And that's not right. 13. Makes things a little bit better. So what's that give me? 20, sorry, 19, bad. 19 minus 6. Okay? So that is the rule then. That is the rule for that arithmetic sequence. That is what generates the 13, the 7, the 1, and the -5. And what I would just, if I were you, would do, maybe on a test or a quiz or whatever, homework, go back and check. Does it make sense? If n is 1, do I get 13 by plugging that in here? If n is 2, do I get 7 by plugging that in here? If n is 3, do I get 1 by plugging that in here? And if n is 4, do I get -5 by plugging that in there? In each one of those cases, I do end up with those results, right? Okay. So I know that that's the rule. Now, what's nice about that is now that I know that, I want to know maybe the 1,000th term. Okay. Well, here's the rule for it, right? So don't I just have to say 19 minus 6 times 1,000? And now I know my 1,000th term in the sequence, which is much more convenient than having to go 13, 7, 1, -5, and keep subtracting 6 1,000 times to get to that 1,000th term, right? But if you did that, you would get the 19 minus 6,000, whatever that is. Okay? Does that make sense? All right, so here they ask you for the 300th term, or they walk you through finding the 300th term. And you find it's -1781. Okay? So if I were to write this list out, 300 terms long, that 300th term is going to be that number right there. Okay? You guys can do this on your calculator. Maybe you've done this before. If I want to like continually let's say I start with like 24. And I want to add to it 4, hit enter, add to it 4, hit enter, and keep doing that. Am I creating an arithmetic sequence by doing that? Okay, and some of you maybe have done that in the past on some type of question, but what you're doing there is dealing with an arithmetic sequence. And how many times I've hit N, or hit enter, I guess, to tell me the term or the location of my sequence, to tell me that N value. All right, so what is nice about an arithmetic sequence, guys, is if I know the first two terms, okay, if I know those two terms, I can find any term I want to, right? Okay, but what is nice is that if I know that term, but I don't know this one, and I don't know that one, but I know that one, I can also find any term I want to. Okay? So what is interesting about arithmetic sequences, as long as you know two terms, you know all the terms. Okay? Now the process of finding them, a little bit more difficult in this situation, but what we end up with is the ability to create a system of equations here in two variables. Okay? And if we conduct this correctly, finding the sequence is really easy if we develop our equations initially, I guess the correct way. What I'm going to do is I see the word arithmetic right away, right? And I know then that when they tell me the 11th term is 52, I know that 11th term is found by using something of that form, don't I? Does that make sense? The fact that it's arithmetic tells me this would have gotten me that 11th term. Okay? Well, we've got some things we can plug in here. It says the 11th term. So if I write A sub 11, right? 11th term tells me 11th position, and that's the N. That's the counter or the index that we talked about. Is equal to A sub 1. Well, A sub 1 is the first term. If I read this problem, do I have the first term? Do they tell it to me? No. Okay? So I don't know the first term. So I'm just going to let it be A sub 1. Plus then, N minus 1. Well, if this is going to find me the 11th term, what would be N for the 11th term? This would be 11, right? So we 11 minus 1. Now, as I look at this problem, I don't have, I can do trial and error because the 11th term and 19th term aren't too far apart from one another. But I don't have a really good idea of what D is, right? So D is also unknown. Okay? So if I look at that, can I combine this to 10 right here? And really have just 10D? So I'll do that. If I look at that, now how many variables do I have up there in that red equation? Is A sub 11 a variable? Is it an unknown amount, the way I've written it? Yeah. Is A sub 1 unknown? Is D unknown? So you have three variables that are unknown, right? If you ever remember back to three variable equations and systems, those are a pain in the butt. So the hope is that maybe we could alleviate that a little bit. We could plug something in to fix this, okay? And also, if it was a three variable equation, we would have to have three terms provided in my problem. And right now, I only have two terms provided. What do they tell me that thing is? 52. So make that substitution as well. So now how many variables do you have? You have two variables. Okay? So now I want to do the exact same thing for the 19th term. All right, and I always write this way. A sub 19 is equal to A sub 1 plus now n minus 1. Well, what is n on the 19th term? 19. 19 minus 1 would be 18, right? So 18D. But the 19th term, that thing right there, can be replaced with what? 92. And you're not asked to do this on the final, but you are asked to do this in a couple questions in your homework. Okay? You have a system of two variables there, right? And the way you develop it every single time will always set itself up for elimination real easily because of the A sub 1 being the constant in both, both of these. Okay, that A sub 1 is constant, meaning that's the same in both. So what I do then is that you can kind of approach this two different ways. You can either multiply one of those equations by a -1 and add, or you can just subtract the two equations. I like to multiply by a negative and add. So when I do that, I get 40 here, right? Negative A sub 1 plus A sub 1 gives me 0 A sub 1, so that will disappear. And now I'll get, what, 8D there? So now my difference is what? 5. Okay? So that process targets finding that difference between knowing the 11th and 19th term. Allows us to find that 5 is what's going to get you from the 11th to from 11th term being 52. I keep adding 5, so I go 57, and then I go 62, and then 67. I keep doing that. If I do that up to the 19th term, that 19th term will be 92. Does that make sense? Okay. So now you know the common difference. And whenever you have a system, you take that variable that you just found and plug it back into either one of the initial equations to find the other missing variable. Okay, so we'll go back to the original one. 52 is equal to A sub 1 plus now 10D. Well, 10D is 50. So now what would A sub 1 be? 2. Okay, so now we have the ability to say that for this sequence, the rule for it is every arithmetic sequence follows this rule. It's A sub 1 plus n minus 1 times D. Obviously, that gives me 2 plus 5n minus 5. That gives me -3 plus 5n. And that's my rule then for this sequence. Okay, and it shows you that you, regardless of which two terms you're given, you have the ability, though in this case, obviously, there's a little bit longer of a process, you have the ability to find a rule for every single term in that sequence. So if they ask you what the 1,000th term is, -3 plus 5,000, right? Okay, so 4,997 would be that 1,000th term. And I don't have to write the list out. Okay, we don't have to do any trial and error type stuff to determine what the rule was. We have a direct procedure of being able to do that. Is that doable? Okay. All right, so with these sequences as well, we like to do partial sums. Okay, and here's where it gets kind of nice to have some formulas. I'm not gonna, the formulas are not hard to prove, but obviously we don't have enough time to do that the next day or so. I think I do have some videos online that walk you through the proofs of these formulas. But let's say that I have just the counting numbers, 1, 2, 3, 4, 5, 6, my natural numbers, through 100, and I want to add all those together. Well, nobody wants to sit on their calculator and go 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to 100, right? It's going to be time consuming. All right, and if you're a person that says, okay, I can do that, that's fine. Well, what if I change to 1,000 or a million? You don't want to do that, right? Okay. So what is nice is that we have a formula that's going to allow us to do this. Okay. And the formula essentially comes from taking a summation of a arithmetic sequence and going through some of the calculus concepts that I showed you in section 13.1 today, and manipulating the sum and eventually coming up with a formula. It's actually two formulas because of the way we can reduce, make some substitutions. It develops two formulas that we can use. So this kind of walks you through the procedure, and we end up with the sum of the first nth terms to equal this thing here. Okay, and then we can simplify that to this thing here. And I'm going to generalize this on the next page. All right, here are your summation rules for arithmetic sequence. So the first thing I do is recognize that it's arithmetic. And then when they want partial sums, you can use those two things. Okay? Now, don't memorize these. It's on the formula sheet for the exam. But what they say is that if I know, and we have to decide which one we want to use, this one here, I got to know n in both of them. So I got to know, and it's used in both of them. So if I want the first 50 terms, here with the first 100 terms, whatever, add together, n is going to be pretty easy for us to locate in the problem. Okay? This one here, you need to know what a is. Okay, so you need to know a sub 1, your first term, and you need to know the common difference. Okay? If you have that information, okay, if you think about what that means, is you have a list that might look like this. 1, 3, 5, 7, a list like that. Do you have the first term there? Do you have n, or can you come up with n? Or not n, d, sorry. Do you have d? Okay. And now if I tell you you want to add the first 50 together, you would have n to be 50. Does that make sense? So let's say that, and those are just numbers, right? So let's say we want to sum, and the next question asks this, on the next slide, says we want to sum the first 50 terms together. The first 50 odd terms. Okay? So we're finding s sub 50. We know it's arithmetic, so we can use this thing here. N over 2. So n being 50. So 50 over 2 gives you 25. 2 times a. A is your first term. So 2 times 1, right? 2 there. Plus then, n minus 1. What is n in this case again? 50. So I go 49 there. Times d. What's d in this case? 2. So s sub 50, it's going to give me 100 in here, isn't it? 98 plus 2? 25 times 100? 2,500. So if you were to write the first 50 odd terms, 1, 3, 5, 7, all the way up to 99, that'd be the first 50 terms. If you do that, add them all up, you get 2,500. Is that doable? Okay. Now, why would I ever want this formula here? Okay. Well, we have the ability, if we talk about the odd terms, okay, isn't this a rule that provides you the odd integers? If n is 1, 2 times 1 minus 1 is 1. If n is 2, so the second odd integer would be 2 times 2 is 4 minus 1 would give me 3, right? So 3 is the second odd integer. I do it with n being 3, so it gives me 6 minus 1 is 5, so that's the third odd integer. So that rule is giving me this. Okay? So the reason I might use this formula is if I have this. Now the 100th term, sorry, the 50th term would be 2 times 50 minus 1, which would be 99, right? Okay? If, you see how the difference between these two statements? 1, 3, 5, 7. I don't know that last number in my sequence. 1, 3, 5, 7, ellipsis, 99. Now I know that last term, right? If you know your first and last terms of your sequence, you want to use the second formula because it's a lot easier. You can still use this one. There's nothing wrong using this one. I can still find A, N, and D from that list. If I look at this, that is simply saying you take the average of the first and last term. A sub 1 and A sub n, those are your first and last terms. You divide by 2, so that's the average of those two terms. And then you multiply by n. Okay? So if I do this, S sub 50 is going to be 50 times A, when they say A, they're implying A sub 1. So 1 plus A sub n, that'd be the 50th term, so 99. Take the average of that. Well, it gives me 50, doesn't it? What's 50 times 50? 2,500 again. Okay? So those two formulas, you can use that first one every single time in any arithmetic sequence, but that second one might be kind of a shortcut thing, provided that you have enough information. You have that last term in your sequence. Okay. Tomorrow we'll do geometric sequences or talk about them somehow. Hopefully have some time to work on that exam, talk about the exam. I'm going to put the video together of that during third period and try to get that posted before you guys leave school today. So you can look at that and